So we have some terminology to talk about, we have some concepts to talk about, but normally when I talk about these things, I draw on the board. So that's what I'm going to do now, like I normally do. So here is a cell in your body, okay? And inside I have, let's say 100,000 sodium. Actually, let me change that. 100,000 potassium, and outside I have 1,000 potassium. Okay, K plus equals potassium. It's a salt that we have. It's a metal that we have in our cells. Now, I know that that seems kind of odd that I'm drawing that ahead of time, but what I'm about to talk about kind of deals with that, so let's go back and forth. Terminology-wise, we have cells that are polarized, meaning that there is a voltage difference between the inside of our cell and the outside of our cell. So if we look here, I have 1,000 positives outside of my cell and 100,000 positives inside my cell. I would say there is a huge difference between what's outside versus inside. In fact, there's a 99,000 positive difference, because if I go from inside with 100,000 minus what's outside, which is 1,000, that's 99,000 different. In other words, I have 99,000 more positives inside my cell than I have outside. So that difference in charge is why we say our cells are polarized, because just like polar means there's a difference in charge, or when we talked about water being polar, we said it had partial positive and partial negative. These cells are polarized. Sorry, that's the washer. So resting membrane potential. That's the voltage difference between the inside and outside of a cell when the cell is unstimulated. Nothing is happening in the cell at this time. And normally for our cells, for our neurons, that's between, for our muscles, that's between -70 and -90 millivolts, which is just a unit of measure. So if I have a probe inside my cell and a probe outside my cell measuring the charges, when my cell is resting, when nothing is happening, I'm not contracting it, it's just sitting there, that's the resting membrane potential. Okay, that's what this number is. Now, two things establish that membrane potential. One, the differences of ions inside versus outside of the plasma membrane. So remember I said I have 100,000 potassium inside and only 1,000 potassium outside, yes? Well, that's one difference. Another example, excuse me, of things being different might be that I have 1,000 sodium inside my cell and 100,000 sodium outside. Na plus is sodium. It's that particular ion, okay? When it comes down to it, the difference between what's inside and outside is caused because I've got different numbers of ions on both sides of this membrane, and that difference creates that resting membrane potential. Now, sodium potassium pump. We talked about this in chapter 3. Chapter 3. We talked about, no, actually, yeah, it was chapter 3. I'm not lying, it was chapter 3. We talked about the different types of channels that you can find. And one of them that we talked about was a pump, an ATP powered pump. So sodium potassium pump actually works in your cell, okay, by pumping out 3 sodium and pumping in 2 potassium. So the pump out 3 sodium, so 3 pluses out for only 2 potassium, 2 pluses, because remember each potassium is 1 positive, each sodium is 1 positive, for only 2 positives in. Now remember, a pump uses ATP. So I've got this pump working to pump 3 sodium out and only 2 potassium in, 3 sodium out for only 2 potassium in. If I keep doing that, I'm going to end up with less positives going into my cell than are going out, meaning that the outside is more positive than the inside. Okay? So this right here already establishes that the inside of my cell is going to be slightly negative compared to the outside, just because I have this pump working and I'm only bringing 2 pluses in for every 3 pluses out. So this is one thing that helps me to establish that membrane potential, okay? The membrane permeability characteristics. So remember we talked about leak channels, and leak channels did one thing all day long. They leaked. So I'm going to erase this for a second. Well, actually, I'm going to erase it, period. If you need to see that again, you can rewind it. Leak channels are called leak channels because they are always open. That's why we call them leak channels. So if you think about leak channels are always leaking. Now I'm just trying to black out the membrane of the cell. This isn't really what's important. What I'm going to draw in a second is what's important. This is a lot easier to do when I'm working at the board because the dry erase marker comes off a lot easier. Okay, so potassium. I have leak channels for potassium, and they're yellow, color-coded, right? Meaning that potassium can get into and out of my cell through the leak channels. Now, how many leak channels do I have for potassium? Leak channels for potassium. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I have 14 leak channels for potassium. That's a lot of leak channels. Pretty much any potassium that's anywhere around the cell has an access point. Now, let's talk about sodium. So I probably do have leak channels for sodium, but if you look at the number of leak channels that I have for sodium, it's a lot less. For sodium, leak channels for sodium, I have 3 leak channels. If we're talking about a cell only having 3 entry points or exit points for sodium as opposed to 14, that's a lot less, meaning sodium has a harder time finding an entry or an exit from this cell than potassium does, because potassium has so many more leak channels than sodium does. So when we talk about this resting membrane potential, when we talk about the membrane potential in general, the permeability of the membrane, how leaky is that membrane, determines the membrane potential. In this example, sodium is not really likely to just have access in and out of this cell because I don't have a lot of sodium leak channels. But when it comes to potassium, I have a ton. So potassium has the ability to get in and out with no issue. So what's the permeability characteristic of this particular cell that I drew? Well, it's permeable to potassium because I've got a whole ton of leak channels for potassium, but not really permeable to sodium because I only have 3. So when I talk about the membrane permeability characteristics, that's what I'm talking about. Potassium can leak without any issue because it's got plenty of leak channels. Now, the resting membrane potential, this abbreviation is just for this up here, is measured in a unit called millivolts, okay? And normally it exists at between, like I said, negative 70 and negative 90 millivolts. It's negative because, remember our pumping 3 positives out for only 2 positives in, that actually makes the inside of our cell slightly more negative than what we see on the outside. So, ion channels. This is one of those blocks that I showed you on that slide before. Ion channels are ion channels. They never ever change. Just like I said, a chair never changes. A chair is a chair, same thing. So leak channels. Leak channels are always open. For our purposes, that's how we're going to leave it. They are always open. They are always available. Now, is that reality? No. But for us, that's how we're going to think about them. Ligand-gated channels. So in a ligand-gated channel, you have the ligand, which is the key, and you have the channel. When the ligand isn't bound, the channel is closed. When the ligand is in place, then the channel opens and it will allow things to move. Voltage-gated channels. Remember, voltage-gated. Voltage is the thing that allows things in and out. You've got this ball and chain that has a specific charge to it, right? When the inside of the cell has the same charge as that ball does, the ball stays in the channel to get away from it because it doesn't like sticking around with the same charge around it. But when the inside of the cells, when the inside of the cell changes charge, if it's opposite of what's on this ball for the ball and chain, it'll move. And it'll move so that our channel opens and things can move through that channel now. Again, ligand-gated, voltage-gated, leak channels. They're always the same, whether I'm talking about them now or in Anatomy and Physiology Part 2. It doesn't matter. They always work the exact same way. So, action potentials. Action potentials. Action potentials are a change in charge inside my cell. So, going back, remember that I was measuring what was happening inside of my cell here, right? So when I do want my cell to change what it's doing, like a muscle contracting, I have to actually change the charge that is inside of that cell. And when I do it in a grand fashion, That is called an action potential. So, there are two phases to an action potential. And you can see them here. Where I'm measuring, remember I said between -70 and -90, so this is at -85. I'm measuring what's happening in the cell. When that inside becomes more positive, we call it depolarization. When the inside goes back to where it started at the resting membrane potential, RMP, it's called repolarization, okay? So during depolarization, the inside of the cell becomes more positive and the outside less negative. So we see that when this pops up like this, the inside is becoming more positive than the outside. During repolarization, think of the word rewind. It goes back to negative to the resting membrane potential. So, cell stimulation causes voltage-gated sodium channels to open. So, voltage-gated channels, that's this guy right here. Okay? They're gated. Yes? All right. So, cell stimulation causes voltage-gated sodium channels to open, and sodium will influx into the cell. So, I'm going to come back to here for a second. I'm just going to draw a simple gated channel, okay? Meaning that I have something that I can open and I can close. And you can see that there is something that's there, but it's closed up. So I've got these gated channels. Now with the gated channel, when I'm at resting membrane potential, the gate is closed, which you can see there. Okay? You can see that there's something blocking things from moving. Okay, there's a block there. When I go through depolarization, though, I actually open gated sodium channel, voltage gated sodium channels. Okay? Meaning that these open. Now, movement always goes from high to low. Where is sodium high? Look at the numbers. I've got 100,000 sodium outside and 1,000 inside. High to low would be 100,000 to 1,000. So when I open those gates, this 100,000 starts to go into my cell, into my cell, into my cell. Because I've opened all of these gates, it actually now has access to the inside of my cell. As I start flooding positives into my cell like this, the inside of my cell starts to become more positive. And the more I allow in, the more positive the inside of my cell becomes. That is depolarization, when those voltage-gated sodium channels open. Okay? Sodium influxes, it pours in. Okay? Now, there is something called threshold. that you can see right here, okay? Threshold is basically the all or none point, where if I get to here, I'm going to fire no matter what happens now. If I don't get to here, if on the other hand I change a little bit and only get to about here, I'm going to come right back down to resting membrane potential. I don't go all the way up to my action potential up here because I didn't reach this all or none point. The best way I can think to describe it is a gun. If I have a gun and I'm going to fire the gun, right? And that hammer falls on the flint on my bullet, the gun's gonna fire. It's not like if I release the trigger after it's already hit, the hammer has already hit the bullet, I can go, okay, take backsies, it's not gonna fire now, or it's gonna get sucked back into my gun. It doesn't happen that way. Once that threshold of the hammer hitting the flint on that bullet happens, you're done. That gun's firing no matter what. Same here. Once I reach threshold here, I'm going to have that depolarization no matter what. That's what threshold is. It's that all or none, you're gonna get an action potential, okay? So, an action potential is the reversal of charge difference that stimulates muscle contraction. This big change from -85 to about +20, that change in charge is basically your muscle signal to go, you contract now. And it contracts because it got that signal. Stimulation is strong enough to cause all the permeability changes responsible for the action potential. In other words, I reached threshold and enough positive sodium got in to get me to here, so now that's gonna happen. Okay? So, if the inner cell keeps becoming more positive, eventually voltage-gated sodium channels are gonna close. Eventually, they kind of go, okay, we're done. And I'll show you how in just a minute, and voltage-gated potassium channels start to open to restore that resting membrane potential. Remember what I said about I get up to the top up here, and then I come back down to my resting membrane potential. This is because of potassium, specifically voltage-gated potassium channels. Okay, so again, going back, here I had all of these voltage-gated sodium channels that opened up to allow all of this sodium to rush into my cell, right? Well, I also have the gated potassium channels, and while I only had 14 of the leak channels, I have all of these extra voltage-gated potassium channels as well. And when the inside becomes positive enough, just like these guys opened, these guys get the signal and they open up. And as they open up, look at the amount of potassium inside my cell versus outside my cell. Remember, this is diffusion, so it only goes from high to low. So if I have 100,000 inside and only 1,000 outside, high would be 100,000, low would be 1,000. So it would be moving from inside my cell to outside of my cell. So all of a sudden, this potassium that's at 100,000 starts getting basically kicked out of my cell. So the amount of positive inside of my cell is starting to go down because I'm leaking potassium out all over the place. When that happens, this number that's really high up here will start to drop. And repolarization, remember rewinding, happens. That is because eventually my voltage-gated potassium channels open to get back to this resting membrane potential. So I've got depolarization. The inside becomes more positive, the outside becomes less negative because voltage-gated sodium channels open up and there's an influx of sodium. If I reach threshold, this all or none point here, then I have an action potential and muscle contraction. Once I have reached a certain number or a certain amount of positive inside the cell, then the voltage-gated sodium channels close, the voltage-gated potassium channels open, and I start leaking potassium, repolarization. And I eventually will return to my resting membrane potential, back to this negative 85 that I was at to begin with. So, if an action potential isn't reached, the cell returns to resting membrane potential. If I try to pull the trigger on a gun and the hammer doesn't cock back and fall forward and hit the flint of my bullet, then nothing's going to happen. I'm just going to go back to the gun not firing. Action potentials actually do travel section by section down the cell. They propagate. Action potential frequency. So see this symbol right here? This is a lowercase lambda, okay? Lowercase lambda is just a shorthand for the word frequency. So if you see this, know that I'm just saying the word frequency. So frequency, what does it mean? How often? How often does something happen? How frequent is it? So when I talk about action potential frequency, I'm talking about how many action potentials per unit time. If the action potential frequency is high, so is the strength of stimulation. If I keep hitting it and hitting it and hitting it and hitting it, then it's going to have a pretty strong stimulation. The action potential frequency is high. It results in an increase in the strength of muscle contraction. The nervous system controls muscle contractions by sending action potentials along axons to muscle cells and stimulating the muscle cell action potential itself. Remember what I said about skeletal muscle. It can't just contract because it wants to contract. It contracts because it gets a signal that it's its turn to contract. Okay, so